All right, welcome everybody. Thank you for coming. It's day 2 of Research Week. Hope everybody's having a great week. We know that our theme this year is Research is North Carolina. So today we're going to be celebrating research in North Carolina. And it's an exciting topic that has unfortunately significant gravity for the population of our state and really beyond, and an area in which we have historic strength and exciting new developing strength. So my 2 favorite things that our university does is mobilize our research findings to help improve the lives of people in North Carolina and beyond, and also identify areas of future need in terms of expertise and future opportunity in terms of jobs, and make those opportunities to get that education available to our students. So there's an amazing panel here today who will talk about some things that we've been doing for decades and some things that we're just developing now. And a lot of it is geared towards being able to be responsive with data and data science to help improve the things we do to manage hazards like flooding. And we'll talk in particular about Western North Carolina. Hurricane Helene is one that's in everybody's head. One of the most recent ones that really brought things to mind though was in 2021. Hurricane Fred, a little more localized, flooded the town of Canton and was really catastrophic. And then poor Canton got it again in 2024 from Helene. So at one time, 5 or 6 years ago, I used to field a lot of calls from the media asking me to talk about the Southern Appalachians as a climate haven. Well, we don't believe that anymore. And we now know that they have similar, if not maybe even greater risks than the coastal end of our state. So research is about North Carolina. We know North Carolina is amazing from the mountains to the sea. We have natural beauty. We have natural systems that are largely intact. But accompanying that and living in those places is some associated risk. So how can we use data going forward? How have we used data in the past? And what opportunities do students have to join in this exciting field? And with that, I will hand it over to Dean Daly.
Can everybody hear me okay? Good. So I'm Stan Holt. I'm the Dean of the School of Data Science and Society, at least for now. And some of you know this inside joke. I'm just very pleased to be here with some of my favorite people on campus, and I have a lot of favorite people on campus. But I would like to ask each of them to introduce themselves, and then I have a set of prepared questions that I will pummel them with, trying to see if we can find the data behind flooding and risk. So let me start on the left.
Hi everyone, I'm Greg Charaklis. I'm a faculty member in the Department of Environmental Sciences and Engineering. I also direct something called the Institute for Risk Management and Insurance Innovation.
Hi, I'm Helena Garcia. I'm a PhD candidate in the E3P program, so the Environment, Ecology, and Energy program. And I study where has flooded in the past in North Carolina, and then what are the decisions people make after floods, like do they move or do they stay?
Good afternoon. I'm Rick Ludick. I'm a faculty member in Earth, Marine, and Environmental Sciences. I direct the Penn University Center for Natural Hazards Resilience. I spend, my primary offices is down at the Institute of Marine Sciences on the coast, so you don't see me up here too often, but I work predominantly in coastal flood modeling.
And I'm Jackson Mink. I've been in the School of Data Science and Society for getting toward 2 years, and in the Computer Science Department the entire millennium. I actually joined in the fall of '99, just in time to have Hurricane Dennis that sat off the coast of North Carolina for a couple of days and poured tons of rain. And then Hurricane Floyd, about 2 weeks later, flooded out the eastern part. And got interested in how long it would, so that referring to the technological innovations from North Carolina was really the first state to partner with FEMA and sort of take over making flood insurance risk maps, which had started in about 2000. They thought it was going to take 2 years to process the LiDAR data that they had flown for the entire state. It took them 7. And I got interested with one of my PhD students, and he made LAS Tools, which was a very popular LiDAR, public domain LiDAR processing software. So I know the history and have not been active in the present, but I've always been interested in this data, and I've done a lot of stuff both here and in University of British Columbia, which was my faculty position before that, working with forestry and sustainable forestry and spatial mapping.
So I'll kick off the first question, and I think we can just let anybody respond who cares to, and maybe for the first one, maybe we need to get everybody to respond. So what data do you need to use in your work? And it's a compound question, how do you get it, and who controls the access to it?
So for our work, we're often most interested in trying to translate extreme environmental conditions into financial endpoints for people. And so in order to build the models and build the understanding of those systems, there's plenty of natural system or natural science related data that we need. Fortunately, we're pretty good at collecting much of that, right? We've gotten better at that over time. It's not only on the ground measurements, but there's satellite-based measurements and so forth. Financial data is harder to get a hold of. And that's really for the kinds of work that we do, is really the challenge. Who has it? Sometimes it is centralized. Claims and policies data on flood insurance are housed within the NFIP, within FEMA. Hard to get. We have had some success getting information there. But really, that's only information on insured flood damages. Another big challenge is figuring out what the damages are at all the uninsured places, because there's many more of those, and nobody tracks that. So all the information that one needs to try and make those assessments is often housed in individual households, things like that. Makes it a lot harder to get a hold of. So.
I also use some of that flood insurance data, so it may be a natural segue. But yeah, I use a lot of like hydrologic and environmental data that's usually publicly available. But then in terms of data on like structures and people and like who experiences flooding, that can be harder. In North Carolina, we have a really great buildings data set that the state creates, which is unique to our state. Some other states have them. But then in terms of questions about like are people moving or who is experiencing flooding, that is usually proprietary data that you have to purchase from, for example, like credit bureau sources that track and compile people's addresses over time.
So I do physics-based modeling of how water moves, and so and I'm mostly thinking about coastal areas. So and of course, it's for this to be interesting and topical, it needs to get not only move in the water, in the ocean, and the estuaries, and the rivers. It needs to get up onto the land, and then interact with the structures and whatnot. So I need a really high quality data sets that describe the terrestrial and submarine areas, and so high resolution data of that sort, the LiDAR data that was just mentioned, works well on the land. It's processed properly. It doesn't work so well because it doesn't penetrate the water. So there's there's challenges and other ways to get that, but the truth is that there's actually a gap. The further that we have pretty good data underwater in the kind of the coastal areas, the further you go kind of inland. So we're okay in the estuaries, but as you start to get up into the feeder rivers and streams, particularly if they're not major navigation rivers, then that data is largely inferred or non-existent, and so that's very problematic. And so I spend actually a lot of my time trying to convince the people that might collect data of that sort, like the U.S. Geological Survey and or NOAA, that this is an area that they ought to focus on, and no, they don't need to bring a 200-foot long ship up into those areas to collect the data. There's probably better ways. I've had a lot of entertaining conversations about how to do this over the years. So that's a key part of me being able to create a model that is accurate and representative of a real area like coastal North Carolina, and I spent a lot of time doing that. The other area that I really need information is sort of on how to make, what forces the water to move. And so I don't model all the way to the sun and the hydrologic cycle and all of that part of it. I kind of focus on the motion of water that's hit the land, if you will, and or in water bodies that exist there. So I need to know information on the winds. I need to know information on precipitation. I need to know the things that actually create water in places where it might not otherwise be, or push water around or move it into, again, areas where it might not be. So we have a lot of that data through the Weather Service, although it becomes more and more challenging to get the more severe the storm events are. And so our ability to predict either on a particular event basis or in a statistical way what those more extreme events look like is difficult. And as such, we oftentimes, even if we can do the physics modeling really well, we oftentimes don't know what to tell our models, what conditions to put into our models and to make them run. And so you'll oftentimes hear, 60% of the flooding that occurred was outside of the quote-unquote floodplain. That's probably a failure of imagination in terms of, or a statistical understanding of what the atmosphere and what the weather patterns are likely to create in those areas.
And I'm more of a methods person, so I like interacting with people who have data and have questions, and sometimes the data and the questions don't match up, and if, as a methods person, can I make that work a little bit better? It's amazing to me over the years of how more and more data is available in different formats, and sometimes it's not the right format. Sometimes it makes certain questions much more difficult to answer, and so that's where I like looking. But I also wanted to notice that how each one was saying, data is often collected for certain economic reasons by somebody with certain reasons, and sometimes it's hard to pry out data or even get data collected unless those are the drivers for somebody's priority.
So each of you all mentioned data gaps, but I want to push a little bit harder on that. And so the question I want to pose is, what are the biggest data gaps that prevent us from anticipating where the next unexpected flooding might occur? So what is it that we can do to fill those gaps? What could we decide as a society that we wish to collect or pay for or dream in order to be able to anticipate, for many reasons, where a flood is going to occur?
I think this one's for you.
So I don't model future floods. I look more in like the recent past. But I think one thing that we actually don't have like good information on is how our development patterns and people are going to move in the future. So yeah, like kind of what was mentioned before, like people moved to Asheville because it was called a climate haven, and then there was this unexpected event. And so it's really hard to predict how those things will happen in the future. And there are some people over at NC State like doing, creating scenarios and creating like future land use maps for, and like looking at the different scenarios. So I think data science has a role to play out all of those decisions that could be made about where people are in the future.
Rick, I know you're chafing at the bit.
Well, I think Mike's opening was just ideal. The Appalachians are a climate oasis. Probably not. And so, the first thing I would say is, as the climate changes, it's hard to extrapolate from the past into the future. And so it's, we really have a lot to learn about what the future looks like and how to translate that into societal and human impacts. So I think that's a big part of it. Again, severe weather events don't happen that often, and as such, they're difficult to even conceive statistically. And my colleague Richard Smith, who's here, works as a career working on those kinds of things, and but it's just hard to anticipate. I mean, it's fairly easy to anticipate what the middle of the distribution looks like. It's really hard to anticipate the tails, and so that's a real challenge. And as such, not only is it hard to do statistically, but we as people don't think that way very much, and so we just don't take them off. We don't give them as much potential for likely to impact us as we probably should. And so there's a societal and an emotional and a personal aspect of just how we think about some of these rare events. And then, lastly, I would say it's well recognized in the meteorological community, at least, just how hard it is to predict precipitation. I mean, it is really difficult because it has spatial variability, it has structure to it that's just a real tough problem, and so at least inland flooding, which is largely dependent on, again, these extreme precipitation events, can be really challenging to verify.
Those are great answers. Shifting a little bit to data science itself, I think this is getting to the methods. Can you just tell us a little bit about kind of where you think data science needs to head to prepare for the next major flood, and tell us how your work might be doing that already?
Well, one thing is, lots and lots of data and machine learning is being done on images and text. A lot of people are less familiar with spatial data. And one of the things, the power of GIS is that different types of data can be very difficult to combine, but when you assign it spatial coordinates, you can combine data by just showing that, oh, these data are happening at the same location, and you can get insights from that. Figuring out what those insights are and how we can continue to do that as we scale up large amounts of data. There's so many different characteristics of the data that is collected with spatial locations and some of the gap between on the land and under the water and things like that. That's all very special things that sometimes need to be done. And so it's much harder than just pixels in an image or large amounts of text, I think.
So we spent a lot of time trying to think about solving one of the problems that the state has come to us about, which is keeping people in their homes after a flood. I think as many of you have probably seen in the news, there's still a significant amount of people from Florence in 2018 that are in FEMA trailers or some form of alternative housing. So we spent a lot of time thinking about this issue of mortgage default, or how many people actually abandon their homes for financial reasons. And so one of the big challenges, as I think I alluded to earlier, well, there's two issues there. One is who floods, and we spent a lot of time with Helena and her group, her two groups, but she works with both Dr. Tony Sebastian and Dr. Miyuki Hino, focusing a lot on where it floods. And then we think a lot about the impacts of those floods after they occur. And one of the things that's really been missing is an understanding of uninsured damages, because nobody monitors these things. And so we had some very clever graduate students and postdocs that developed a machine learning approach that takes information on insured damages, which is pretty sparse, and combines that with information on the environment around each home, so distance to water body, in and out of the floodplain, variety of characteristics, and then property-specific data on first floor elevation, square footage, date of construction, and we can put that into a more continuous estimate than of uninsured damages, which we use with a combination of other information on property value and so forth to come up with an estimate of how vulnerable a home is to flooding in terms of increasing the potential for mortgage default or home abandonment. And so there's a lot that you can squeeze out of these existing data sets with more advanced analytical techniques. And so we've tried to use that in a way that helps us answer some important questions.
And I'll just add, it's amazing what machine learning weather models can do these days. Again, I live on the coast. This year we had 2 storms that were headed, when they were in the northern Caribbean area, they were headed straight at us. And the question was, were they going to continue on that trajectory or turn off to the north and to the northeast? And I can, for the first year that I can remember, machine learning based hurricane track models were available, kind of widely available to the public. And I can tell you that we had Umberto and Imelda, and then before that, Aaron. So both of them had this kind of towards the coast and then curved off, not at the last second, but pretty close. And I can tell you that the machine learning hurricane models picked that up and predicted that earlier in time than the weather services and even the European weather models did. So it's amazing what, and now the machine learning models are trained based on years worth of physics-based weather models. And so I think that there's a huge potential for the use of AI and ML in augmenting, supplementing, and just flat out making physics-based models better.
Interesting. Let's dig into that a little bit more and talk about the tools and models that you all use, and particularly we want to get to the future very soon. But can you say more? For example, why, Rick, since you already hold the microphone, why do the machine learning models seem to be able to do this earlier than other models that you see out in the field? I'm really curious. Just
If I knew the answer to that, I would probably be spending more of my time doing machine learning models than physics-based models. I think that I'm not sure that the community knows that answer, I wish I could answer that question. I can tell you that there are other areas which are a little bit easier to understand that machine learning is really helpful. To run a full physics-based model can take hundreds or thousands of compute hours to do, and one run. Oftentimes you want to run thousands or tens of thousands of those model runs to build up statistical databases. And what we have found is that we can run maybe a few hundred physics-based models, train an ML model on those physics-based model outputs, and then use that to fill in the gaps and do that very, very efficiently. So we can, whereas it probably exceeds the practical compute time to do it all with physics-based models, kind of, again, blending the two is now a standard of practice in trying to identify hazards and build up risk. So that's certainly an area where I think it's started to mature. But why it is the hurricane models, the ML hurricane models got it better than the physics-based ones, I'm interested too.
okay. Anybody else want to talk about models and methods?
So just in terms of like reconstructing where it flooded in a specific event, so physics-based models, they take a lot of data to like create, calibrate, validate, and a lot of computation hours. So for example, like I used machine learning trained on the insurance data we mentioned earlier to model and create flood maps for 78 events between 1996 and 2020. And yeah, some of those events like Florence and Matthew and Floyd have been modeled using physics-based models, but only about 6 or 7 were usually the largest events that have that data collected. And those are the ones that we typically want to learn the most about. So we've been focusing on those. But focusing beyond the biggest events is also important for thinking more comprehensively about where flooding is happening.
That's a very good point. Let's talk about translating our research. How do we go about convincing people, particularly communities, that we have the kind of information that they really need and that they should be paying attention to it? So talk to me if you don't mind, or talk to us if you don't mind, about that challenge. Because I think data science is a lot about telling the story and telling it well. And that could be visually or textually, or maybe there's other ways.
So this may sound a little bit glib, but if you can't translate your results into either dollars or a health-related endpoint, particularly lives saved, you're going to have a difficult time making the point to a broader audience. Not to your colleagues at a conference, that's a very different audience. But in order to make policymakers care about it, you typically have to move into that sphere, and that's not always easy. I mean, sometimes there's a straightforward way of translating a result into some sort of monetary terms, but often there's a whole chain, a whole system that needs to be understood in order to get to a financial endpoint that people care about, such as mortgage default. And so that's something that I think we've focused on a lot, and we've had a significant amount of success, certainly more than when we were just talking about some more natural science-related endpoints in getting policymakers, both at the state and the federal level, interested in what we're doing.
Very good point. Others have any comments on that?
I'm going to dominate the conversation. I have had a chance to work on flood maps per se, and boy, there's little that evokes more annoyance than a flood map. I mean, it's never right. It's always out of date. Anyways, there's everything wrong with it. When North Carolina redid their flood maps in around 2010, 2011, 2012, the county that I lived in, more areas ended up in a flood zone. Some of the northeast counties, less area ended up in flood zones. And I can tell you that our county government that gets tax dollars in by encouraging developers to build on all buildable land was very annoyed and said, well, in this round, the Northeast won and we lost. And I said, maybe that's not the right way to look at it. I think we won because now we're better informed of what the hazard areas are, and so, we're less likely to have a disaster in those areas down the road. Where I'm going with this is that I basically, got the conversation around, and I've had the same conversation in several different contexts, but this is a good one, I said, is there any data I could show you that essentially would make any difference in the way you think about this? And the answer was all but no. So I think it's really important to recognize the social challenge associated with trying to solve some of these resilience and risk and behavioral problems, and really think so hard about how we can both manipulate data to be as effective as possible, but even what data we need to be trying to generate to be able to make a difference. And I agree 100% with Greg. Money talks. And so if you can get it to a financial endpoint, it matters, but in almost all cases, they see it as being a net financial negative because inevitably it tells them you can't do something, and that they see that as costing them something. So it's one heck of a challenge to try to use data in ways that actually makes a difference.
Yeah, so a bunch of my Data 140 students are here, so this is why, it's not just about data structures, but it's also about the stories and the emotional impact that these stories can have. I do want to say that for us and as researchers, it's usually not the money or the health things, but it's the challenge and the fun of exploring things. But yeah, when you're telling a story to someone who's not intrinsically motivated by trying to understand things, money or health do become important motivators to try and tell that story.
So one thing that Rick said kind of reminded me that not all communities want or need the same data, and we don't always know what kind of data would be most helpful for them. So just as like a really quick example, I was on a team with Ann Smiley and Lauren Grimley, and we partnered with the stormwater superintendent in the city of New Bern, and we were sharing information on flooding during Florence, and he was interested in that and wanted to learn more, but he actually told us, I actually really need to know more about these intense rainfall events that happen a lot, and that's when my phone rings. And I need to be able to talk to people about what's happening. So I think it's important, we were able to go back and run Lauren's model to tell him that information, but we had never thought of that as something to share with them.
So I take from that comment that there's a lot of value in asking the community, what is it that you really want to know before we try to collect the data? So that's kind of a natural segue in looking to the future. We've talked, I know, amongst ourselves about a much more integrated flood prediction system, something that looks longer term and connects a lot of the dots, connects the buildings, connects the structures, et cetera. Is there, and somehow gives an assessment of risk. What are the barriers to building that? Is it all social, or is it some technical things that maybe some interesting developments like drones taking pictures of ash fill can estimate the uninsured damage by looking at piles of stuff and doing image analysis, trying to determine how much value is out on the street?
Just from the drones or just remote sensing and observational kind of data that's getting better and better all the time, I think we still, as researchers at least, really rely on the on-the-ground observational data of a ground truth point to be able to understand how accurate that kind of data from a drone would be. So that can be whether it's a water gauge on a river to help inform how accurate the flood model is. Having those are still going to be really important in the future too.
I guess, a cynical question, but who's paying for it? So it was very interesting to me that, I really liked the idea of spatial mapping and flying the entire LiDAR for the entire state. Small aircraft with, laser rangefinders in early 2000 was quite a novelty. North Carolina was really the first state that was doing this. And it was for insurance maps, which is the people who are willing to pay to know about the future floods, because they're the ones that are paying out when the flood occurs. And so the state and the insurers. So that was, to me, a realization that, if we want an integrated flood, there's a lot of data challenges to be solved. And that takes money, and so who is going to wind up paying that money because they benefit from this integrated flood mapping? And it would be nice if it's us collectively, because we all benefit, but sometimes it has to be a more specific person or entity to get the ball rolling and get over the activation energy needed to bring things together.
I'm glad you went first, because I think you are exactly right. Who's paying is really important. This is a huge problem, and it's a very, may not seem interdisciplinary, but it's definitely very interdisciplinary in the way that science and engineering communities have organized themselves. The coastal modelers tend to be a very different community than the hydrologic inland modelers. The folks that are paying attention to insurance are in, I don't know if they're physical science or social science. They straddle that for sure. I worked a lot in the last handful of years with engineers that spend a lot of their time in post-damage building assessment, trying to get data on first floor elevations and really understand how a wave this big in this location will do this much damage to this structure, but it's a complete different community. And so, again, there's a challenge associated with someone coming along and saying, I got enough money to put on the table to get all of you guys together to integrate. And even if we did, the tools that we have are designed to really start at one end of our natural discipline and go to the other end of the natural discipline. So you've got to be able to interface essentially between the areas. And so, historically, just the way that the science and engineering has developed makes it even a harder challenge, I think. And so, I think we have more of these events. North Carolina has been hit by, certainly going back to Floyd, but Florence and even Matthew, that were both big coastal and inland events. You just can't ignore Harvey in Texas and even other ones in Florida. You can't ignore, if you really want to tackle that problem holistically, you got to get, you can't just do it, this group does this part of it and that group does that part. You have to get it together, and so more and more we're getting it together, but there's still a lot to be done in that area. And I have to, again, wonder the extent to which this is done by folks that have traditionally done their own little pieces and then try to plug, again, the nuts and the bolts together, or whether AI and ML comes in and just says, I'm going to suck up all of the knowledge in this area and suck up the knowledge in this area and suck up the knowledge in this area and integrate it in some way. I don't know whether that's realistic or not, but it's interesting as to wonder whether that has that capacity.
This is reminding me of something a mathematician John Conway said is, he does a lot of things with puzzles and games, and he says, when you become good at stuff, this is real math, because when you become good at it, you find out what it was you were supposed to have been thinking about. And I was thinking about that in, your, as sort of a response to your physics-based modeling versus allowing the AI to find certain patterns, which can then be extended with physics-based modeling to be able to do the modeling. It's figuring out its own pattern to know what it should be thinking about. This also comes with any of you students who are looking to, make some impact on some area. Some of it is you have to know what is out there and what is in between in the areas that you're looking at, and become enough of an expert that you can see how to combine two things. You learn what you should have been thinking about, or what somebody should have been thinking about had they wanted to combine these two things from the start. And if you can find the innovation in there with machine learning tools or without machine learning tools, that's where you can really make a contribution that it's always at the in-between things. It's often not at the big overall problem that everyone can see, but it's the in-between things.
So, Greg, I'm going to move in a minute to the kind of where the field is going, but before we get there, do you think we can do a better job of measuring community impact? In other words, what it means for a community to make a decision about a zoning law, or about a decision to move or not move, or repair or not repair a road? I mean, is there a way to put it into the terms, the endpoints that you've been talking about?
I mean, communication is important, right? But even if someone understands, I think the point was made earlier that you've got to get people to respond. You can understand something and still not respond. People respond to incentives. And I think what you're seeing increasingly as we get better and better at evaluating these risks is that the groups that have the ability to influence behavior are taking more advantage of it. Whether it's the insurance companies, which need to understand what the risks are, raising insurance rates in high-risk areas, or whether it's groups like mortgage lenders. When you buy a house, if you have a mortgage, the bank owns part of your house, and they are incentivized to have you understand what risks you're taking. And so if you're buying in a higher risk area, what you're starting to see now is the interest rates are going up for those sorts of mortgages. Those are the kinds of things that influence behavior over time and do it at a macro scale. And so I think government will always play a role, and government putting a moratorium on development in a certain area is certainly one tool. It's probably a tool that hasn't been used terribly successfully. I think now you're starting to see these more diffuse approaches to influencing people's behavior take root. And our research can certainly influence those groups. They're sophisticated, they're in a position then to take actions that don't necessarily limit people's behavior, but put them more in a position to pay for the risk that they're taking, as opposed to sending it more broadly.
If nobody else wants to weigh in on that, let me ask you, where's the future of this field? And kind of tell us where you think things should be going and maybe how students can get involved.
I'll just say that I think we will be driven increasingly when it comes to climate-related risks by the decisions that are made by groups like the insurers, like the mortgage lenders, like the credit ratings agencies, groups that are capable of taking the more sophisticated understandings of these risks and translating them into something that influences people's behavior.
I guess I would say, at least at UNC, I have been constantly pleasantly surprised with how many people across different departments and programs are thinking about flooding from their own perspective. So like yesterday, I was with some people who study cancer outcomes, and they're really interested in how flooding can impact the timing of someone getting their first treatment after they're diagnosed, or even pharmacy closures. And they're looking for better data, which we can provide, but I think it's because North Carolina flooding is such a big issue, there's a lot more people thinking about it outside of just like the environmental sciences than you would think. And I think a lot of different disciplines have skills and things to bring to the problem of what happens after floods beyond just people who model it and think about it all the time.
Yeah, I think a key feature is building interfaces between the things that we do well, and so that we can integrate and get away from, I can tell you how deep the water is, but I have no idea how much damage it caused, kind of things. And so I think that there's a lot of need for that. Again, I think there's a lot of unknowns and potential to figure out how to translate from a world in which it's all driven by physics-based models into a world that's driven much more efficiently, probably by a blend. And I don't know how far that blend goes into machine learning and AI, but there's no question that there's value there, and probably a lot of it. And so I think that there's a lot of opportunity there. And I really think that, again, getting a more end-to-end capacity, I think it's what you asked about earlier, Stan, about kind of a whole framework of building a whole integrated modeling. I think that is important so that you can actually get all the way to consequences, and then start talking much more effectively to insurers and people that hold that know a lot about the financial aspect of it, and they can then say, hey, could you tell me this more effectively than we do now, as well as the health stuff. I think getting to those societal endpoints better than we do now is a big opportunity.
Rick, I'll just freelance it a little bit here. I'll never forget the discussions that we had after Katrina, and I think it was the Coast Guard that was very interested in trying to understand kind of what the more global impacts would be on shipping, and where you're going to get your next shipment of coffee, where you have to refine gasoline. The level of complexity that really is called out, if you really want to understand how we operate as a society or at a more global level, that's probably 14 or so years ago. I can't remember.
The whole maritime security industry, all of that goes along with that is enormous. I mean, it's just, and it's, we don't see it, but, we don't think about it, but everything that shows up on our, all of the commodities that we purchase somehow down here. and a tremendous amount of it is shipped, and all of that is an aspect that we really haven't even mentioned at this point. You know, and then so much of that also, people live, in order to have a port, you have to have people that run the port. In order to have a Coast Guard station, you have to have Coast Guard people that run that.
Yep.
And so all of those people live in potentially risky areas. And so there's all of the stuff that goes along with just being able to support the people that are required to do what we think of as maybe more technologically mechanized process. So lots of challenges out there.
Lots.
Plenty of potential for undergraduates at this point to have a very long, fulfilling career.